uh, a vegetable oil, that is jatropha we have taken, and an alcohol, methanol, to produce biodiesel. Okay, so biodiesel is just kind of trying to give you some brief about the biodiesel, where we are looking for some substitute of diesel fuel. Okay, so that is why we are trying to get the biodiesel extracted from various vegetable oil or animal fat and getting reacted by, so this is triglyceride, and then it get reacted with alcohol. So the trans-esterification reaction takes place, and the biodiesel is produced. So it has several advantages like non-toxicity and lower level of carbon monoxide or total carbon and particulate matter production, no sulfur content, and easy and safe handling. Okay, so so this reaction, this trans-esterification reaction to produce biodiesel is being studied over the decades, because the idea is to replace the diesel fuel without much change of the existing design of the engine. Okay, so basically, and today we can see that various blends of biodiesel are available. Okay, so maybe 20% biodiesel can be added to the diesel fuel, 40% biodiesel can be added to the diesel fuel, and we can use that. So for this advantages, this reaction is very attractive. But the point is, when you try to carry out in a batch reactor, you face certain limitations. Okay, so the limitations are, so this is a reaction that is being shown, and we use some catalyst for it also. And what is the limitation? Let us first discuss it, why we are not particularly interested in carry out in specifically in case of, let's say, in a batch reactor. So this is basically uh, is a mass transfer associated with the reaction. Okay, so the molecules, let's say the alcohol molecules, they need to diffuse through. Okay, and then the reactions will start. So the diffusion process itself, so if you mix alcohol and triglyceride, that is uh, the oils, so they are not miscible. Okay, so if you take a this two mixture in a batch reactor, or any reactor for that matter, and you keep it aside, so you can see two layers. Okay, so the reaction only happens at the interface, and the molecules need to diffuse to the interface. So the resistance of diffusion is very much high in such cases. Okay, so there is a mass transfer limitation. So I guess chemical engineers can correlate when a mass transfer is associated with a reaction. So the mass transfer, we say it mass transfer limitation, because the mass transfer is the now governing, dominating the entire situation, because it's the slowest phase. Okay. Also, if you could like to look at the reaction itself, it's a reversible reaction. Okay, so the product are also forming, and they react back to the reactant. So that is another challenge. So due to this high resistance of mass transfer, what it takes a very longer time to complete the reaction in a biodiesel. So you typically take 2 hours or 3 hours to, and the yield finally what you got is very less. Okay, so the product of this reaction are, of course, the um, monoalkali ester, that is the biodiesel that we call, and along with it uh, some glycerol is being produced. So the separation is another challenge, but that is okay. High molecular ratio can be utilized for to shift the reaction, okay, to more to the product side. But the major challenge is this too: mass transfer limitation, which results in long reaction time. Okay, so for this, there are several process intensified reactors are being proposed. So what are they? They are maybe ultrasound or cavitation assisted reaction. So we have one cavitation assisted reaction setup in our lab. So after the class or maybe the tutorial today. If you wish to visit, you can see the cavitation assisted reaction setup also, though we are using it for some other reaction purposes. Okay. Then the separation, as I say, the separation is another challenge. So separation can be coupled with some technologies. Then you can use the mini and micro reactors. Where the mini and micro reactors are coming to the picture in this case? Because when you lower the scale, what happens? The diffusion length is now reduced. Okay, so the species, let's say, that is need to travel to the interface for the reaction, the traveling path is less. So the mass transfer resistance, that is the slowest of all the stages in this particular reaction, are now being taken care of through this miniaturization of the reactor. Okay, so that is why we more focused on this one. So this is already being discussed. Okay, so what are the typical parameters in such cases of production you can think of? So depending on, so what are my challenges? My challenges is first to take care about the mass transfer, then about the high reaction time, which is the result of slowest mass transfer step, and of course the purification. So what modification for parameters, input parameters in a microreactor we can think of? So it may the design of the microreactor itself, and as we have discussed in the several last classes, that the injection type that matters in such small reactors for the distribution. So the injector type itself, of course the flow distribution. What is the type of flow distribution? We will discuss more in this class, that how the flow distribution matters. Molar ratio for reaction, temperature. So this reaction happens at a particular temperature of 55 degree to 65 degree centigrade, around that. Okay, below the boiling temperature of boiling point of methanol. And of course catalyst concentration, that is another parameter because it is a catalytic reaction. So these are the parameter more or less we have studied. Of course, we have not studied temperature. We have taken almost a constant temperature, okay, which is reported mostly in literature. Other parameters in some way or other we have discussed. So this is the setup we have used. Okay, in the experimental setup we have taken a serpentine geometry. Now let us take a small break over here and discuss why the serpentine geometry, why not a straight one. Okay, so last class Professor Angeli has pointed out that the process itself in the reactor in such kind of miniature channels is often a laminar flow. Okay, isn't it? So she has mentioned that it's a laminar flow, so it is very easy to model because no turbulence modeling is involved. That is very true. So you have lowered the scale, the diffusional resistance has been gone. So you have, but you have laminar. So the transport process is now governed by the diffusion, molecular diffusion itself. It's a low Reynolds number process. So the diffusion, the mass transfer is governed by molecular transport. Okay. So there are scope for improvement of the transfer rate in such reactors. And how you can improve the transfer rate further, that there lies your innovation. So generally 3 methods are reported. You can try something else also. Once, so what is the idea? Idea is to how to create a local turbulence in your channel, in your reactor, so that further enhancement of the transfer rate can be achieved. So how to create the local turbulence? You can use a change in direction for the flow. You can use a change of area for the flow. You can use some kind of flow inversion, so that, or some presence of some solid particles here and there, so that the flow rate or the mixing at the local level, okay, can be enhanced, and which can result in further enhancement of the transfer process. Okay, So that is the idea. That is why we have taken the serpentine geometry. The work of, so you may ask why you have not checked the change in area for that matter, or why not you have, I mean, taken the some other methods. So that methodologies for change in area or some other weightability induced phase inversion, that I will take up in the next lecture when we will discuss the intensification of mass. Okay, so here we have used two things that we have taken several reactors, but all serpentine reactors. Okay, and let us first discuss about the setup. So here is your serpentine reactor, and the reactor is itself maintained in a typical oil bath, so that a constant temperature of up to 55 degrees is heated from the bottom, okay, through electric coils, so that 55-degree temperature can be maintained. So we have two fluids. First is the jatropha oil, second is the methanol and mixed with KOH. Okay, so these are again forming a homogeneous mixture, and this is being pumped and injected in this inside the reactor, and we have a pressure transmitter to record the signals. After the reaction happens in the reactor, this it is coming out and it is getting uh, separated under gravity separation, and we get two different uh, product. One is biodiesel and the glycerol. So they are phase separated, they are separated under gravity separation. So the initial condition are given for the jatropha and methanol. So jatropha is forming the continuous phase, methanol is forming the dispersed phase. Okay, so to make point out two things. One is the viscosity. You can check the dispersed phase viscosity is very light. Okay, in comparison to the continuous phase, and here the liquid glass, okay, because this is made of glass, so liquid glass contact angle is given. Now in another column I have mentioned liquid stainless steel contact angle. Why this is mentioned, we will show you now. So this is our first setup. Okay, so what we have total length of this serpentine channels are around 2.66 meter. Okay, and each turns of 500 millimeter. So the diameter is typically 2 in a diameter, and is forming a curvature ratio of 12.7. Okay, details of so this is a photographic view. Now this is another variation of this setup only. So what we have done and why we have mentioned the contact angle with respect to stainless steel is for that matter that we have in this particular one, as I say, there is sometime change in area or change in area of the flow path maybe can be helpful. So we thought maybe injecting a twisted stainless steel wire inside this particular serpentine channel may be helpful. Okay, let us try that what will happen to the reaction. So we twisted two stainless steel very thin wire inside this reactor. Okay, and so that we get some undulation and it form like an annulus. So this is why the contact angle with respect to the stainless steel is also mentioned. Then we have changed the number of turns, and we have two other setup we have made. And for comparison, we have taken a straight tube of same inner diameter of same length. Okay, no turns. So these are the final comparison. So R by D ratio we have gradually reduced, and we have compared with straight one with the R5. So before going to the reaction, first let us understand the hydrodynamics, because it is the hydrodynamics which are, so where you think the reaction will take place? At what location? Here, okay, at the surface of this slugs, okay, where your two phases are in contact, there only the reaction could take place. So their distribution matters a lot. And what the other thing it matters how long the phases are in contact. So that is given by residence time. Okay, so two things matters. One is the distribution, which is indirectly specifying the specific area of contact. Okay, it is the distribution, so you could yourself figure out the specific area of contact for this type of thing and specific area of contact of this type of thing, or specific area of contact for this type of dispersed droplets, all are, and so is the residence time. So basically, and how we are getting this distribution? By just modifying this mass flow rate or volumetric flow rate. Okay, so we are giving the input of volumetric flow rate, and that way can be, and the volumetric flow rate can be, you can correlate with the molar flow rate. Of course, you know the molecular weight, you know the density, so you can calculate the molar flow rate. Once you know the, so you can actually influencing the molar flow rate, you are influencing the specific area of contact, and you are influencing the residence time also, right? So, so these are the distribution we got. One is slug, second is slug with some droplets, third is a kind of transition regime. So some kind of coalescence of the slug happens, and slug takes a long structure, and some droplets, obviously due to high interfacial shear, they detach and they form in the continuous regime. So this is called intermittent slug, and finally the droplet dispersed. Okay, so as I mentioned earlier, there is nothing very smoothly dispersed, but yes, you can have droplets, very fine droplets. Sometimes they join and try to form some bigger one. Okay, so that is what we call droplet dispersed. So this is for the first setup. So when you inject a stainless steel wire, so what will happen? So let us go back to the weightability data here. So what is the weightability data? What is my dispersed phase? The wire is the at the center of the tube, and my dispersed phase is methanol. Okay, so just for continuous and methanol droplet that you have, the stainless steel, with the stainless steel, they are having again a low contact angle. So what they try to do when they have something like this, so the drops are try to, what we observe, try to stick on this particular stainless steel, and when they are closer, so you can see a large slug is actually being almost stuck at that particular surface. And gradually what happened, there are two phenomena can happen. If the slug is of, let's say, smaller size, and it is being stuck, so sometime with the increase in flow rate of the dispersed phase, it is joined by some other drops or slug, forming a further long structure. Okay, that is increase of inertia for the dispersed phase. If I instead increase the inertia for the continuous phase, what will happen? The interfacial shear is again acting on the particular dispersed phase is increased, and you may observe detachment of droplets, dotted drops from the slug. So these two phenomena may happen, which gives rise to two different regime only in this particular annular structure. One is slug droplet, second is droplet dispersed. There are more uniform type of structure that we can see from this. Okay, so this is happen when you have something inserted in this. So till we don't know that whether it going to improve the reaction yield or not. So this is, and this is the straight one. So just for comparison, we have given the straight one. We have just again, so no dispersed phase is being mentioned. Okay, we have noted only slug and slug droplet. Similarly, this is for R3 and R4. So what is new? What is new? This one, this observe, this flow pattern. Okay, so this is observed for R4. What is R4? R4 is the test section where you have very less R by D. So what happened when the R by D ratio is lesser? They're closely packed. Okay, so then there is a sudden change in direction of the flow, and you have at the downstream, let's say first at the after the bend. So you can see this is first bend. Okay, this is after the second bend. So after the direction change in direction happens at the first bend or the second bend, so there is a tendency for the slugs to join. Okay, and also some continuous phase is being, because the dispersed phase is made of methanol and it is having very less viscosity. So what the continuous phase drops are being invaded this particular long structure. They go inside, okay, inside this long structure of methanol, and you could see there are small drops of continuous phase are observed inside this long, slightly distorted structure of what we call encapsulated rivulet. The term encapsulated, why we use, because of the existence of the small drops of continuous phase inside the secondary phase. Okay, so this is the effect of R by D. Now let us see what will be the effect of all these things on the flow regime map. So for the flow regime map, in order to, because we have taken different RYD and different, not different, let's say, um, structure of geometry. So we have tried to put it out in terms of non-dimensionalized number. One is Weber and second is Onsurge. So it's a product of that we are giving. So all the forces are taken care of. So this is more or less what we have discussed. Okay, so only two flow regime observed for R2, while 4 observed in R1. So this is the case where we have the annulus. Then, so this is some comparison are given. Okay, and this is, I guess I have already mentioned that in this particular geometry, what happened that the methanol drops are spread and tried to stay on the surface on the steel wire. So that result in, if you increase one phase inertia, it could result in forming a long structure. If you increase the inertia of the continuous phase, it may uh, uh, due to it may result in formation of dotted droplets. So that is the main difference in here. And this is also we have discussed, that is the formation of this kind of rivulet structure and encapsulation. Okay, so this is another observation, which is, so we have now 5 flow pattern in case of the R by D 1.5. So what is their effect in case of so in case of this one, finally let us move to the reaction quickly now. So we have measured the yield using a GC, and let us first analysis. So this is the percentage uh, yield of the biodiesel that is given, and this is the continuous phase Reynolds number, and these are at different dispersed phase Reynolds number, that is, of course all are superficial, are given superficial velocity based Reynolds number. So these are given, and now let us analyze. So what is the observation? So let's say for, if we follow for a given Reynolds number, for a dispersed phase Reynolds number, it for all cases is maximizes, then it decreases. First increase, maximum attains a maximum, then decreases. This is true for all cases, but you could see the maximum of yield is happening closer to our, the Reynolds number of the continuous phase closer to 1. Okay, so let us first check why this happened. So if we can go, if we could check here, the residence time of this is this. Okay, for 0.5, this is slightly increased, but the 0.5, what happens that if you can check, that there are very less formation of the droplets. Okay, so the specific area of contact in such cases are less, whereas for case 1 there are number of droplets are formed, so the specific area of contact in this case is higher. So you may argue, okay, why not in Reynolds number 1.4, the number of droplets are even more, isn't it? So we expect this increase of specific surface area further. Then why the yield has been decreased from here to here? Right. Decrease of residence time. Okay. So when you go from here to here, what you are increasing is the phase velocity of the continuous phase. When we increase the phase velocity of the continuous phase, the corresponding residence time decreases. The time that two phases are in contact within the reactor decreases. And as a result of which, you may get the decrease in yield. Okay, so that indicates the existence of an optimum situation in terms of both the residence time and the specific surface of contact. So both need to be optimized so to get a maximum yield. So this trend is true for all cases. Okay. Now the observation is that so we inserted in weaving the stainless steel wire inside the serpentine structure, assuming that its further reduction in area and possibly may in some cases it may happen to increase the yield, but the reverse happens. Okay, when we inserted the wire, the maximum yield that we obtain in case of the reactor 2 is basically less than reactor 1. So this happened because there is a tendency for the methanol to sit on the stainless steel wire, okay, and forming a long structure. When the long structure is formed, then your specific surface area is again disturbed. Okay, so that is why the maximum yield also in this R2 is being reduced. Okay, then in comparison of a single, I mean straight serpentine channel without any insertion. Okay, so maximum yield we have observed in all these 5 reactors in R3. Okay, so it's very close to around 97 or 98%. R4 also having the similar, um, yield. R5 yield is pretty low. So you could see if we take a straight reactor, this is not even 80. Okay, this is not even 80, and we get more than and close to 98, 97% of yield in a serpentine reactor. So, so I would like to mention here that we have tested this reaction in a batch reactor also. And for the similar type of yield in a straight reactor, the batch reactor takes around 2 hours. Whereas this happens in 20 minutes, almost, taking all the separation and all these things into account. Okay, so that is the advantage you can have in a small channel reactors, and further you can modify it through some change in direction, make it serpentine. Okay, but again, so what is the deduction till now? What is the R by D that you can take, and why there is an increase in yield for R3 or R4? More mixing due to presence of, I guess, or to know or not, in single phase flow, if it is passes through some serpentine channel, it observed there is a flow reversal. Okay, so if it's primary direction of flow in this way, at the bend there is a in the macro channel, due to what happened in the presence of centrifugal forces, so there is a secondary flow that we observe in reverse direction. So at bends, what it will happen is almost is a counter current operation. So this is flowing this way and the secondary phase is flowing this way. The heavier phase is flowing this way. So some kind of similar thing is happen in this particular cases also, in such serpentine channel also. So we noted some kind of disturbance wave, okay, at the bend, which is giving rise to a secondary flow in the reverse direction. That it you can take off as a counter directional operation. As chemical engineers, we all know the counter direction operation is always having a higher efficiency than the co-current or co flowing uh, setups. So for that, this reaction yield is higher in R3 and R4. Okay, so so we got that, okay, in R3 or R4 setup we have a maximum yield. But what happened that maybe then how we can what to choose? So there is coming another parameter, that is, so this is all thing we have discussed. So this is so we have, let us skip this, maybe there is, so this is the biodiesel we have produced and tested. So what type of reactor to select? What type of reactor to select? We have another parameter coming to the picture, that is related to energy. What is the pumping power you can use for? So for that, we have estimated viscous dissipation. Okay, how much viscous dissipation is being noted for each of the cases. So for that matter, what we have observed, that obviously for the higher is your R by D ratio, the higher you can go for the viscous dissipation. So taking consideration of this viscous dissipation, we have selected R3, optimized condition, because R4 has two disadvantages. One is tendency to forming the encapsulated rivulate structure, which is not very good, having a specific area of contact for the reaction. And more is the interface, more you can expect the pressure. Okay, so the pressure is also high because the R by D ratio is also going lower. The pressure is also higher for R4, and that is why the optimum R by D that we have selected is 3. Okay, so that is how we have taken care of this optimization design of the reactor. Okay, so these are some observation that, of course, the viscous dissipation is higher in R2 because of this insert and its diameter is getting reduced, followed by R4, R3, R1, and this is so wrong. This will be R5. Okay, R5 is the straight one. So viscous dissipation is almost 1.5 times higher in if you place the wear. Okay, so this too increases the viscous dissipation, and among this R4 having the higher value. So for this, all this condition, this particular optimum condition has been chosen. Now, if I have some time, quickly I would like to mention that we have done two more parametric variation. One is the catalyst variation. Of course, we need to do the optimization of catalyst. Here we have used 2% of catalyst. Then we have actually carried out that from without any catalyst, starting from 2.5 percentage of catalyst, and then we have optimized it. So as we have optimized the length. Okay, so we have taken the reactor 1, then we have gradually added single unit of turns, and then we have increased the length, and then we have coming to the conclusion that this much length is optimized length. After this much optimization has been done on the reactor 1, then only we have taken a further optimization through this insertion of the wear and the modification of R by D ratio. Okay, so the idea is what you need to understand is that you may take any innovative measure for that matter to obtain increase in either mass transfer efficiency or yield or like that. But the idea is you have to check all the conditions in the sense that you need to check whether I am increasing the energy consumption abruptly or not. Okay, that we will discuss in the next topic also, that how to take care of that. I may reduce it, the diameter, okay, from 2 mm to 1 mm to 0.5 mm, but is it worthy? Okay, how much increase of efficiency or yield I am getting by spending so much of energy? Okay, so that is one aspect. So that is why the other thing that what need to be done is that the viscous dissipation or the energy consumption is also need to be taken care of while you are designing. Okay, with this,